Good morning. So let's recap what we have learned on Wednesday. On Wednesday, we basically talk about three topics, right? The first one is, these three are all related to how to address point, direction, and the plan in the unit cell, right? So for the point coordinate, we use QRS to represent a point in this unit cell. For the direction, there are 4 steps. I hope you still remember. The first one is the direction need to pass the origin, right? Origin. And then after that, you need to do the projection to the X, Y, and Z axis. And then after this, you need to make it become a smallest integer for these 3 numbers. And then after that, you need to use square bracket to make it like this. So you have 3 numbers, and then you will have square bracket. So this is to present a direction for this direction, okay? And of course, if you have 4 axes, for example, like a tetragonal structure, so you will have U, V, T, W. So you can do something like this: square bracket 1, 2, 0, square bracket, or square bracket 0, 0, 0, 1. And of course, you understand this number can 4 axes. The point in the 4 axis unit cell can translate to 4 axis hexagonal structure, right? So this can transfer to you have a kind of equations to transfer these numbers to become these numbers, right? Okay, and after that we learn a family of directions. For the family of direction, we use this Kara bracket, UVW Kara bracket, to represent this and this. They are belong to the same family member. They are belong to the same family, right? Okay. So it's 1, 0, 0, 1, 1, 0, 0, 1, 0, 0 here can represent the same direction. Okay, so this is what we call family. Okay, and the third topic is we need to address a plan, right? And there are 5 steps for you to determine these 3 numbers. Okay, the first one is the plan cannot pass the origin. Okay, the origin, you cannot pass the origin. And after that, you have to do intercept. This plan will intercept to the x-axis, y-axis, and z-axis. For example, for this plan doesn't pass through any points in the z-axis. So that means what? That means it's infinite, right? Infinite. Okay, so this is intercept. And step 3 is you have to do reciprocal for these numbers. For example, this is half, so reciprocal is 2, right? If this is reciprocal, if this is infinite, you reciprocal it, and then it becomes 0. Okay, so as a result, you can get a number like this. Oh, sorry. And then after that, reciprocal, right? And then you do the reduction to make it become the integer. Okay? And finally, you have to do enclosure. Enclosure is what? Enclosure is parenthesis, right? Parenthesis. This parenthesis, this one, parenthesis here, right? Okay, parenthesis HKL, 3 numbers. And of course, you will have 4 numbers. That means represent a hexagonal structure. Okay, so you can parenthesis 2, 3, 0, parenthesis, or parenthesis 1, 0, 0, 0, 1, parenthesis. And of course, this plan has a family, right? So a family of plan, we use brass bracket like this. Brass bracket HKL brass bracket like this. Brass bracket 1, 2, 3 brass bracket. So these are the 3 important topics you need to learn, and this will, for sure, this will be in your final exam paper. Okay. All right. So I hope you you understand this, and then today let's move to another topic. That is atomic arrangement and interplanar spacing. What is atomic arrangement and interplanar spacing? So let's start from FCC 110 first. This is a, if you say 110 parenthesis, that means what? This is a plan, right? Not a direction. So if this is a unique cell, and 110 will be 1, reciprocal of this 1 will be 1, reciprocal of this 1 will be 1, reciprocal of this 0 will be infinite. So it's 1, 1, infinite. Infinite means that it doesn't have a path, there's no intercept between this plane and the z-axis, right? So that's what you can see. FCC will be represented like this. And let's address this atom as A, B, C, D, E, F. Okay? So this is FCC parenthesis 110. So this is 110 is this plane, right? This plane. Okay, if we take a look of this in 2 dimension. So this is 3-dimensional presentation, and this is 2-dimensional. So you can get A here, B here, C here, D, F, E, F. So you understand this is the one. And this is the plane. Okay? So, and then this is a 2-dimensional repeat unit. I hope you should still remember we learned this last week, and we have this in your Kahoot question, right? Okay, this is repeat unit. That means this one will repeat. Okay. So the point here I want to let you know is that you need to transfer 3-dimensional structure to become 2-dimensional structure. That will be easier for you to understand. It looks like this here. Okay. How about, so this is FCC 110, right? And how about BCC 110? It's the same. Okay, so BCC is 414. So you have A prime, B prime, C prime, D prime, E prime. As a 2-dimensional structure, you can realize this is the one. Okay, you might say, Professor, why do I need to learn this? So let's take a look at FCC 110 and BCC 110. What's the differences between these 2? So this is FCC 110, right? This is BCC 110. So you understand this is a repeat unit. This is also a repeat unit. And you understand in this repeat unit, there are more atoms occupied in this repeat unit. And there's less. So that's why we are going to learn something about this. Right, so compared to FCC 110, BCC 110, let's take a look of the different planes in the same crystal structure, like BCC. So BCC 100, BCC 110, and BCC 111. Right, so as you understand, if you take a look 2-dimensionally, it looks like this. Okay, it looks like this. And then you might say, well, Professor, why? You understand this, right? Because this is this. And you understand this because this is this, right? And you might say, well, Professor, why, if we have 111, 111 here, why it looks like this? There's nothing in the center. Because of what? Because 111 plane does not pass through the core. This one, the core of the center atom. Okay? So it doesn't pass the core here. So that's why we regard this plane has no atom in the center. Okay? Right, so the first one we need to know is interplanar spacing. So if we treat it two-dimensionally, you will have interplanar spacing. So interplanar spacing is what? The distance between the adjacent plane of the same middle index, HKL. So if you move the plane parallelly, and then for unit cell A to unit cell B, and the distance between unit cell A and the unit cell B is the interplanar spacing. Okay, so for example, let's take a look of 0, 1, 0. So what is 0, 1, 0? 0, 1, 0 is, so 0, right? And then it's infinite. So infinite in its direction. 1 is here, right? And then reciprocal 1 is here, right? It's 1. And 0, reciprocal of 0 is infinite. So infinite, infinite, and 1. So infinite, infinite, and infinite, and infinite in 1. And so this is the plane. Of course, this plane doesn't pass the origin. Right? So however, if you move this parallelly, you can put the origin to this, become origin plane. Right? Or you can put this to here. That means what? O plane, right? O plane. So this is the same 0, 1, 0, or 0 minus 1, 0, right? So between this, the distance between this and this, that's what we call interplanar spacing. The equation you need to know, ladies and gentlemen. Please remember this equation. This is not difficult at all, but I want you to remember this might be in your final exam paper. So what's A? A is the H length, right? This A is H length, and then divided by root H power 2 plus K power 2 plus L power 2. What's K? HKL. HKL is this one. This one is, for example, if I show you this, for example, if I say please find out the interplanar spacing of the plane 0, 1, 0, then you put this is K, this is HKL. So you put this number here, and you got A. So 0, 1, 0, right? So root 1, that will be 1. So as a result, this spacing is A. However, I'm sure you understand. I won't give you this number for your final exam, in your final exam paper, right? I must give you a little bit more complicated number. Anyway, so please remember this equation and bring your calculator. So this is another. So if I say, please calculate the interplanar spacing of the plane 1, 1, 1. So you need to put this number here, right? And you got this, and you get this equation, and you understand what's the interplanar spacing. Okay. So let's take a look of the D010 and the D020. So what's D010? You already know 010 is this one. So this spacing between the two parallel plane is this, right? How about 020? 020 means that reciprocal, that's what infinite. Reciprocal of 2 will be half, right? Half of the B, half of the Y, right? And then reciprocal of 0 will be infinite. So this will be half. So if you have origin here, this one represents the plane. And of course, because this is only half, so you just move parallelly. And this will be D020. Easy, right? So this will be half A. Half A. And this will be A. Okay? So that means that every 0, 1, 0 plane is a 0, 2, 0 plane. So this one can be regarded as this one can regard as this one, right? So every 1, 0, 1 plane is a 0, 2, 0 plane. However, every 2, 0, a 0, 2, 0 plane isn't a 0, 1, 0. Why? Because this one doesn't belong to here. This one, of course, yes, but this one doesn't belong to here. That's easy. So how about D111 interplanar spacing? D111, you just put a number here, right? So that will be A divided by √3. Okay. So according to this equation, you will understand if the HKL increase, and of course A is a constant, right? HKL increase, the D will be decreased. Okay, for example, if we increase the number of this HKL, and then the D spacing decreased. Okay, that's for your information. I'm sure you understand this. This is very easy. So after we understand interplanar spacing and two-dimensional repeat unit, this topic is very important to let you understand the linear and the planar density as section 3.11. So I hope you still remember we introduced you theoretical density, right? Now we are all talking about density. So there's one is called theoretical density. I hope, do you still remember this equation? Yes, you do, right? You do. Right, so this is calculated the weight divided by volume. This is called theoretical density. Of course, you understand this is a definition of the density. However, this section we want to learn linear density and planar density. What does that mean? Linear density, you need to have a definition. If you have a direction like this, then you want to find out how do you define the density of this line or this vector. If you have a plane, this one plane which is parameter 1, 1, 0, and you want to know the density of this plane, and you need to have a definition. Okay? Right, so how are we going to define this? And why this is important? You know, the density is how heavy. If you think of the density is how heavy. But linear density and planar density depends on how many atoms on one plane. Okay, if you have a surface, you have atoms. You want to calculate how many atoms on the surface. Right, this is called planar density. But if you have a direction like a force, okay, if you have a force and then go through this way to this unit cell, and you need to know how many atoms you will hit, or how many the stress of this direction. So that's why we need to learn linear density and the planar density. Okay, I will give you some examples. So don't worry about this. So let's take a look of the definition of the linear density. So you also need to remember this definition. Okay, so LD stands for linear density. LD is number of the atoms centered on the direction vector divided by the length of the direction vector. So this is, for example, this is the vector. Okay, this is a vector. So you need to know that how many atoms pass through this vector. The numbers of atoms centered on the direction vector. Okay, divided by what? The length of this vector. Okay, you know A, right? You know A, and you know the radius, for example. So this is the definition. So unit of the linear density, this is number, right? So there is no unit. And then this one is the length of the direction vector. So this will be it will be the unit of the length. So let's say that we use nanometer. So the linear density will be the unit of the linear density will be reciprocal of the nanometer. Okay, so let's take this as an example. So a square bracket 110 directions for the FCC. So you want to find out the linear density. So can you do this for me? Okay, if I give you the direction, if I give you the definition, so if we take a look in two-dimensional repeat unit, this is two-dimensional repeat unit, right? So this x, y, z here. So x, y, z, and this is, or you can put it on the bottom face or a top face plane. That's both okay, right? So how many atoms pass through this vector? You have to regard this as only half of the circle, half of this sphere. Right. This vector share another half. So share atoms with one another adjacent unit cell. This is another unit cell here, right? Okay, so this is half. Okay, and this is 1. This is half. So how many atoms? 2. Okay, and then you want to find out the length of the direction vector. 4r, right? Radius 1, 1, 1, 1, 1, 1. So 4 radius. Easy. So if I tell you the diameter of this atom, so you can have a number here, right? How about planar density, PD? The definition of planar density is that the number of the atoms centered on a plane divided by the area of the plane. Again, this is how many atoms pass through this plane, and then what's the area of the plane. Okay. So the density, the unit of the planar density will be reciprocal of the nanometer power 2, right? Right. So let's take a look at the example of the planar density. So the planar density of the 110 here, this is 110. Yeah, 110. Right. So two-dimensional looks like this. So can you do this for me? What is the planar density? So this one has a quarter, right? The quarter of the atom, right? A quarter of atom, quarter. So 4 quarter means what? Means 1, right? And this is half of the atom. So this is 1. So how many atoms? There are 2 atoms, right? There are 2 atoms in this plane. And what's the area of the plane? So this R, see there are 4R. How about this one? I'm sure you know this, right? You already know this one. You already know this one, right? And radius. So you can find out that A related to the R. You remember, right? I hope. So this is FCC, right? FCC 545. So you know relationship between A and R, so you can put something like this here. Okay? No problem. Right. So now this question is very important. I want you to understand why we need to learn linear density and planar density. So this is the question here is the crystallographic plane. We want to examine an atom packing of the crystallographic plane. So for example, if you have a foil, you know, when you are at home, you use aluminum foil, right? 铝箔纸, right? Aluminum foil. And now in this question, we're talking about iron foil. Iron foil. Instead of aluminum foil, this is iron foil. Iron foil can be used as a catalyst. What does that mean, catalyst? Catalyst is the one which doesn't participate in the reaction, but it will reduce the activation energy of the reaction so that reaction can occur or can take place easier. Okay? I hope I told you this before. If you have a friend, he want to introduce you a girl for you. So he invite you and that girl to go to the cafe or to go to a coffee shop, and your friend say, "Oh, how good is this? How good is this girl? How good is you? How good you are?" Right? So as a result, you and that girl become a girlfriend and boyfriend, become a couple. But your friend doesn't participate anything, right? Okay, I should say your friend is not your boyfriend. Your friend is not her girlfriend. Your friend is not your girlfriend. Your friend is not her boyfriend, right? So he doesn't involve any chemical reaction or any reactions. So, but he is the one which is very important to introduce you and your girl, that girl, to be together. Right? So this is kind of the job of the role of the catalyst. The catalyst doesn't participate in any reaction, but he helps to make this reaction take place. Okay? So if you have a catalyst like iron, and you want to have a lot of catalysts, you have thousands of your friends. So you can have thousands girlfriends, right? Which you don't want. That'll be too busy. Okay? Anyway, even you have 2 girlfriends, that will be too busy. You have 2 boyfriends, that will be too busy, right? Okay, anyway, but in this case, if you have a lot of catalysts on the surface, that means the chemical reaction will be quicker, and the chemical reaction will be easier. So you want to have a lot of catalysts on the surface. So which plane is better to have a lot of catalysts? This surface, or this surface, or this surface? Which is 111 or 100 or 100? Which one? That's why you need to calculate the planar density of this catalyst. The question is, draw a plane of the iron foil 100 and 111 crystallographic plane for iron. And you need to calculate the planar density of this one and planar density of this one, and find out which one has the more atoms on the surface. Atoms of the iron on the surface. That means you have more catalysts. And that's the plane you want. Right? So 110 is this plane is called 110, right? 1 infinite. So 100. How about 111? 111 is this one. 1 here, right? So this is 111. Okay. Right, so let's get started. So the planar density of the 100 iron. So because you need to know what's the structure of the iron. So I hope you should remember, if the temperature below 912 Celsius, okay, iron has a BCC structure. So you understand now. You understand BCC structure, right? BCC structure is a 414 atoms in a unit cell. So the planar density, let's define you understand this is a definition of planar density, right? So you made this as a 2-dimensional structure, looks like this, right? Okay, so what's the unit cell? What's the repeat unit? If you take a look of this plane, it's 111, right? 100 is this plane, right? 100 is this plane. What's the unit cell? What's the repeat unit? It looks like this one, right? You might say, well, Professor, I don't like it. I want to draw it's like this. Yes, but you get the same answer. And why don't you make your life easier? Make it simple. And you can do the calculation easier. Okay, this is a 2-dimensional repeat unit. So you need to what? You need to calculate the planar density of this. So this is what? This is, you know, you understand this is radius r and a relationship, edge length and radius. So in your exam, in your final exam paper, I will give you the radius of the iron at room temperature. So you know this one, you already know this number. And what you need to know is the edge length and relationship between edge length and the radius. Of course, you know this already. I talked to you this last week. So radius of iron is 0.1241 nanometer. Okay, so it's just pretty standard here. But anyway, you need to make a definition. You need to put the numbers in the definition of planar density. So the planar density here will be how many atoms in this unit cell or in this repeat unit? Quarter. 4 quarter means what? 1 atom, right? Okay, and then this, the area of the plan, that means a power 2, right? A power 2. So this atoms per 2 repeat unit. And this is a power 2 is what? Edge length, right? Area. So if you put the num r here into this place, you'll get something like this. And then after you do the r is, you put the number 0.1241 nanometer here, and then you got this number, the 12.1 atoms per nanometer square. Now that means what? There are 12.1 atoms in this area. Okay? So if you do the calculation for meter square, that means 1.2 times 10 to 19th atoms in this square meter. Okay, so this is the planar density of 100. So how about the planar density of 111 iron? So 111 iron is here, right? 111 iron is here. The important thing, do you get my point? The important thing is to find a unit cell, or the point is you need to find out repeat unit. And this is, it takes a little bit imagination to understand this one. So let me show you something like this. This is unit cell, right? This is unit cell. And 111 is this, right? 111 is this. Okay, 111 is this. Is this repeat unit? Is this plan repeat unit? No, it's not. Okay, so you need to get this plan, you take this plan out. You know, the blue dot line, the dot line marked in blue color, or the blue dot line here is this one. So this one represents this one, this one represents this one, this one represents this one. Okay, so use a little bit imagination. And how about this one? If this one is this one, this one is this one is this, this one is this one, right? How about this one? This atom is above the plane. This one is above the plane. And this dash circle in this the edge the atom marked in the dash line here is below the plane. So this is the plane, right? This atom below the plane. This is above the plane. This is below the plane. Or this is above. This is below. Okay? So it looks like this in this two-dimensional representation of this 111 iron plane. Okay, so if you take a look, if you take this plane out, and next step is you need to find out repeat unit. Repeat unit. So can you tell me what is the repeat unit? Repeat unit. So this one is this one, right? Okay. So the repeat unit is this one. As you can see, if you move this to this way, it tells you the same thing, right? If you move it upward, it's the same. So this is repeat unit, two-dimensional repeat unit. Okay? So 1 atoms in a plane per unit surface cell. So this is the surface, this is above, this is below. Right, so, and then you need to find out the length, right? You need to find out the length because you need to calculate area. And you need to calculate how many atoms in this area, right? So, and you know that this line is this line, which is root 2 times h length, right? Okay, and of course, if you know this, you will know this. Or if you know this, you will know this. Easy. So this is the height will be equal to root 3 divided by 2a. Please go home and do this by yourself. I don't want to waste your time here. So you can do this. And then the area, can you do the area for me? Area is this one, right? If you test the area will be this times this, right? So this times this, that will be area. Height is this one, okay? And then after that, please do this. And then A will be, you don't know the A, but you know R, right? I just give you the number. So this is what you can get for the area of this unit, repeat unit. Right, so what's the planar density? Planar density is how many atoms in this repeat unit? That's 1, right? 1 here. And then you just put this number in this, divided by this number. And do a little bit calculation. You got 7.0 atoms per nanometer square for a unique cell, for a repeated unit. Okay, and if you want to do this by change the unit from nanometer to meter, this is the answer. Okay, so if this question is in your final exam paper, I want you to use a little bit imagination. I probably just change a little bit numbers, change from copper iron to become copper or something. That's easier. So once we do the comparison of a 100 and 111, which one has a higher planar density on the surface? That means that which one got a better catalyst capability? Okay, so which one? This is 1.2 times 10 to 19. This is 0.7 times 10 to 19. Which one is better? This one, of course. So you want to have a surface of the 100 instead of the surface of 111 on the surface, so that you can have a better catalyst performance. Okay? Right, so another thing is, this planar density of the different silicon orientation. This silicon, the silicon wafer in the semiconductor industry. Okay, they also consider about this. This is 100 plane. This is 110 plane. This is 111 plane. Which one has got a higher catalyst surface area? Which one got the most atoms on the surface? This is one of the consideration. But for the semiconductor, they all consider channel effect. Channel effect means what? If you have a 4 ring atoms, you want to pass through this surface, and this one is easier. For example, if you have a bullet in your gun, right? The bullet will shoot to this surface and easy to pass through the 110 plane. And if you don't want this happen, you need to have a more dense surface, right? This will have less channel effect. Okay, so choose a planar density is very important to tune the property of the material. Okay, so you have different plane on the surface, you have different property of the material. Okay. So why linear density and planar density? I just told you. So linear density and planar density are important consideration of related to the process of sleep. Sleep is another property. Sleep is belong to the mechanical engineering student. They use this a lot because of sleep. Why? Sleep is what? Sleep is the mechanism by which metals plastically deform. So sleep is hua, right? In Mandarin is hua. So sleep, okay? Sleep like this. And interesting thing is normally the things will sleep is this plane is the most dense plane. So that's why it's sleep. So if you find out the most high density of the planar density, high planar density on the surface, on which plane, that is the plane which cause sleep. So we will have this topic in a chapter 4, I think. Right. So I think we need to refresh ourselves again. Right? Everybody is exciting and looking forward to have this, to having this. The following information are easy. We talked about this before. The close-packed crystal structures. You know, when we talk about the surface, of course we want to have a most close-packed surface, and want to have a most close-packed of the for the linear density. That's in terms of the some properties. Okay, so what is the close-packed crystal structure? The close-packed crystal structure for metal is FCC, as I just told you before. So close-packed planes of the atoms, the most efficient packing of the equal size spheres or atoms. Normally when we talk about equal sized spheres, that means we are talking about metal. Okay, so both FCC and the HCP crystal structures is the most efficient packing. So the density is high, right? 0.74. But however, these two present the same packing, but their packing sequences is different. So the differences between two structures lie in the packing sequences. So what is packing sequences? I hope you still remember. If you have a layer 1, which is the sphere A in the A layer, layer atoms in the layer A here, and then hope you still remember, in order to put into the layer B or second layer, we have two choices. One is put the atoms in the B position, and one is put the atoms in the C position. However, for the second layer, let's just put it into the B position. So B here. Okay? You know, it takes me a lot of time to make this cartoon. Okay, so I want you to learn. I want you to appreciate what I have done to you. Okay? So I hope you to understand. That's why you show your appreciation in this way, okay? Right, so if you put the B atoms in the second layer, and now you have two choices. The choice 1 is you put the atoms in the A position in the third layer. Choice 1. The choice 2 is you put atoms in the C position in the layer 3. So the choice 1 is you put it into the atoms in the C position for the third layer. This is what we call FCC. And the phase of this phase is 1, 1, 1. And packing sequences is A, B, C, A, B, C, A, B, C. So the fourth layer, you put it atom in the A position. This is FCC 1, 1, 1 plan. And if you put the atoms in the A position in the third layer, that means you represent the layer of the AB, AB. So this is what we call hexagonal close pack. And this phase is, the plane of this surface is 0, 0, 0, 1 plane. So we call AC, AC or AB, AB. Okay? Okay, this is cartoon just for your information. Let's skip this. Right, and then let's skip this. Okay, this is summary of what I just talked to you. Okay? And let's recap this next week. And now, let's move to the section 3.13. So, in this part, of course, we want to start. You already know the single crystals, because just now I always told you the perfect things, like the perfect. There's no atom missing in the structure, right? There's no second type of atoms in the structure. So it's all perfect. And this is what we call single crystal. And this, in this part, we want to learn something not so perfect, okay, or imperfection. Okay, the first case is, we call it polycrystal structure. Polycrystal structure. So let's go back to the single crystal first. Single crystal looks like this, right? Hope you still remember. Single crystal, single crystal. And this is polycrystal, or you can call it polycrystalline. And this is the ingot for a semiconductor, the wafer. Wafer is from ingot. And the purity of this is all single crystal. It's perfect. Okay, it's perfect. Okay. So the periodic and the repeated arrangements of atoms is perfect, or it tends throughout entirety of the spaceman without interruption. Okay, so this is called single crystal. So is it in nature or produced artificially? So nature, what we call this diamond, right? One of the cases is diamond. It's perfect. Okay, you can make it artificially. This is single wafer, and it's high purity single crystal, and this make it artificially. So single crystal has become extremely important in many of the modern technology. It's very important, single crystal. For example, diamond, important, right? Okay. Calcium fluoride, okay, for some applications. So here is another cases for you to understand. This is the turbine blend. You know, turbine for the engine is very, very important because you don't want to have any accidents. So the turbine need to be single crystal. It's a huge turbine, a blend. It all need to be single crystal. So the country or the company which has this kind of technology, they can dominate the market. Okay, and another case is that a diamond single crystal for abrasive. This kind of diamond can be very strong, very hard, and you can cut something. You can cut something which is not that hard. Okay, or kind of abrasive. So as you can see, if this is not single crystal, this has a polycrystal, and this will have trouble when you put this on the turbine. Okay. So we already know how important is single crystal. Now let's take a look at the polycrystalline material. This is what you just learned, right? This is polycrystalline. As you can see, it's not perfect, but it's not so imperfect. So it's some of the region, this part is perfect, but you have small perfect region and then small perfect regions. So you put all the perfect region together, and then you will have something like this. And this is what we call gram. This is gram. And between gram, there's a boundary, and this is what we call gram boundary. So for example, if you see this looks perfect, right? But this edge is not perfect because this is another gram, and this is what we call gram boundary. So under the observation of the surface of one material, if you see a surface like this, and you can see this is crystal, single crystal, and this is boundary, right? Single crystal, and this is boundary. Right. So how are we going to make polycrystal? Very easy. When you are in a chemistry class, especially for chemistry lesson or chemistry class, if you put super saturated salt in the water, and you cool down the temperature, the salt will become the dissolved salt, which is sodium cation and chlorine anion, will become sodium chloride. It becomes solid from aqueous phase or from aqueous solution. And so you can make this, and so when they become crystal, they are not perfect. So this is the formation. One of the easy way to make a polycrystal is this. So this stage of the solidification of a polycrystalline materials. So imagine when you have a super saturated solution of the sodium chloride, aqueous solution, and you started to cool down the temperature, and you can see some seed come out, and let's regard this as a seed. So one cube here, one square here represent a very small crystal, okay? Or you can regard it as a single unit, okay, unit cell. And then the square roots depicts unit cell small crystalline nuclei we call gram, okay? And then if you reduce the temperature, it become more and more, and crystal become bigger and bigger. So this is what we call growth of the crystallines. So of the obstruction of the some grams that are adjacent to one another. So when you touch to each other, it's not perfect. So the crystal will grow from this side, the crystal will grow from this side. Of course, they have different direction. So in the end, they will have a kind of dead space in its place. Right? And even more, if you increase more, as a result, it becomes like this. So this is what we call gram, and this is what we call gram boundary. Okay? So in the end, there's no space at all for the formation of the polycrystal. So it will look like this, and under the observation of the microscope, it looks like this. This is gram and gram boundary, gram and gram boundary. Okay? So the solidification involves two steps. The first step, the formation of nuclei. You know, small seeds. Okay, small seeds. And then after that, nuclei grows to form crystals and grand structure. So these are the two steps. So start from molten materials or liquid. So you cannot, just now I give a case of sodium chloride, which is in the aqueous solution. But you can regard this if you have a metal, and it's like iron is in a high temperature, and then it was in liquid form. And you reduce the temperature, start with the molten materials or liquid, and you start to decrease the temperature. So when you start to decrease temperature, there's a nuclei. Yes, they are nuclei. And then you reduce more and reduce more, crystal growing, and then in the end, it becomes all solid. Okay? So this is the cartoon showing you here. So polycrystalline is solid. Solids are composed of a collection of the many small crystals or grams. So these grams are regarded as a single crystal. So such materials are termed polycrystalline. Okay? So exists some atom mismatch. Atom mismatch means what? This grow this way, this grow this way. So there's a mismatch here. Okay? This area called gram boundary. Okay? So you have direction of growth in this way, right? For this gram, direction of growth this way, direction of growth in this way. So you have a mismatch part here. So that's what this looks like. So what's good about grain boundary? What's bad about grain boundaries? So regions between the crystals, that's why we call grain boundaries. Transition from the lattice from one region to that of the another, right? That of the other. So slightly disorder. So this is not packing so well, right? If you're talking about the packing sequences, packing density. Right. So in this region, this is a low density in grain boundary, right? Because if we talk about density here, this density is high compared to this part, right? Low density. And this boundary, for example, this is high angle boundaries, because if you go this way, and if you go this way, and this is low, and this big gram goes to this way, and this gram goes to this way, this gram goes to this way. So you have a high angle grain boundary and this low angle grain boundary. Of course, you understand low angle grain boundary get better answer for in terms of the density, right? Right. So what's good and what's bad about the grain boundaries? The grain boundary, as you know, that this part has a higher mobility. High mobility means what? This atom is easy to move because the bonding is not that strong. For example, you have 4 bondings here. 1, 2, 3, 4. You have 4 bondings in this plane. Okay, in this plane. However, in this one, you have only 2 bondings. So the energy is high. So this is more reactive. This atom is more reactive compared to the atom here. Right? So higher chemical reactivity. Okay? And this looks like a channel. So things can go through it easier. Not only you can move, but also some of the things like ions can move from here. So you have a high mobility and a high diffusivity for fluorine atoms to go through this way. There's no way for an ion or atoms to go through this way, but there's some chance for small atoms like hydrogen or like carbon can go through this way, right? So the low density in grain boundary is high mobility, high diffusivity, and a high chemical reactivity. Right, so this is grain, and so do we have time? Yes. So let's take a look of the solidification first. Easy. So what you can see is that the crystal goes to a different direction, especially when the temperature, when you have a solidification, the time getting longer and longer. So as you can see from here, this part of the crystal is called equal axis, which is roughly the same size in all directions. Why? Because it's in the very beginning. So the shell of the equal grams due to the rapid cooling. Rapid cooling is very fast and cooling very fast. So you can have equal axis grams. Okay? But once the time goes by, the gram will grow the direction which is easier to go. So the direction of the growth is perpendicular to the surface. That's why you have a colonel. Colonel is elongated gram. Elongated gram, this is elongated gram. It's a long gram. Okay, so you have a equal axis gram, and you have a colonel gram. Of course, they behave differently because of the side, different direction, right? Because of the side, the shape. So this is called grain refinery. Okay. It depends on what you want to make it very equal. Okay. So I think we have next topic, which is 3.15. I think we run our time today, and I don't have time to talk about this to you. So so that's it for today. I hope you enjoy the lecture today, learn something from me.